Let's build a random forest model in Python to help you better understand how it works. Let's start by picturing the kind of problem a random forest is meant to solve. You have a table of data where each row is a past case or scenario, each column is a feature that describes that scenario, and one final column that holds the outcome you care about, whether that be a simple yes or no label or a numeric value like a score. The goal of a random forest is to take a look at this historical data and turn it into a model that can take the features of a brand new row and produce a sensible guess for its unknown outcome. So for today, let's use a simple credit example. Each row is a customer of a bank with features like income, age, total debt, and the number of missed payments, and the label is whether they eventually defaulted on their loan. At the very beginning of training a decision tree, obviously nothing is split yet and all the customers sit together in one large group. We call this entire group of customers a very impure group of data because the outcomes inside of it are all jumbled together instead of being mostly the same. The model's first task is to take a look at this mixed group and search for a simple yes or no question based on one feature that splits it into two subgroups. To do that, the algorithm tries out many candidate questions of the form is feature X less than or equal to some threshold, such as is the customer's income less than or equal to 50K annually, or is the number of missed payments less than or equal to 1. For each question, the algorithm temporarily divides the dataset into a left subgroup and a right subgroup, and then measures how much more pure these subgroups are compared to the unsplit parent group. In classification, this is quantified with impurity measures, such as Gini impurity or entropy, which are low when the subgroup is pure and high when it is not. By computing for each candidate split how much it reduces impurity compared to the parent, the algorithm can select the feature and threshold that yield the largest reduction in impurity. As soon as the algorithm chooses this best split, the data is no longer treated as a single lump. It is now permanently divided into two branches that will be handled separately. Each of these groups can be called a child of the parent class and are also often called a decision node. Once the first split is fixed, the tree building process is applied inside every single branch using the exact same logic but applied locally. Take the left subgroup, which is all the customers with an annual income less than or equal to 50K. The algorithm again scans possible candidate questions, but this time only using this subgroup of data. It might find that asking, has the customer missed at least one payment, splits these lower income customers into two subgroups that are much purer than the parent group. So if this question gives the best impurity reduction, it is chosen and added under the left branch, creating two more refined buckets of lower income customers. The same recursive process happens in parallel on the right side, perhaps focusing on different features and thresholds because the data distribution there is different. This will continue on and on and on until one of three things occurs. First is that a stopping rule is triggered, such as the coder specifying the maximum depth of the forest in the Python script. Second is having too few customers in one of the nodes to justify a further splitting. And third is finding that no split will give a meaningful impurity reduction, so there's really no point in creating more subgroups. Those very last subgroups at the bottom of the tree are called leaf nodes. Ultimately, every single leaf node has a final classification of will default or will not default. When it comes time to predict for a new customer, the tree just runs their data down the same set of yes or no questions from the root to the leaf and outputs the set classification for that leaf they ended up in. And though this procedure may seem intuitive and flexible, it has a tendency to produce models that are fragile. In machine learning, we call a model greedy if it always picks the best looking option in the moment without looking ahead. Now, because each split is chosen greedily to maximize the impurity reduction at that point, small changes or even outliers in the data can alter which split looks best at that point. In addition, if you allow the tree to keep splitting until each leaf is very small or pure, it will often fit not only the genuine structure but also random noise and one-off coincidences in the training data. So to fix this problem, Random Forest changed up the strategy from committing to one singular tree to building many of them that are deliberately different from one another. Now, to make this the most effective it can be, the algorithm needs to generate a collection of trees that vary slightly from one another. And it achieves this by introducing randomness in two stages of the tree building pipeline that we just learned about. The first injection of randomness happens before any of the trees are even grown. Instead of training each tree on the full original table, the algorithm creates for every single tree a new dataset called a bootstrap sample. This bootstrap sample is formed by drawing rows from the original data uniformly at random and with replacement replacement until it has the same number of rows as the original. Because the sampling is done with replacement, some customers from the original dataset appear multiple times and some don't appear at all. The tree treats this bootstrap sample as its one and only training world and runs the same splitting procedure as before. Another tree in the forest will have been given a different bootstrap sample and it will tend to make different choices. And the second source of randomness appears inside the choice of splits at each node. Now, in a standard decision tree, when the algorithm looks for the best split, it is allowed to examine all of the candidate features and all of the thresholds. A random forest, however, can only choose from a subset of the features at random. When you combine the restriction on features and thresholds the model can use with the variation induced from the bootstrap samples, so at prediction time, the forest asks every tree for its prediction and then either takes the majority vote or averages all the answers. The final classification will help the bank see whether or not you are likely to default, and that will help them decide if they should approve your loan. The key takeaway from random forests is that even if each individual tree is somewhat noisy and overfits on its own data, the average of many trees is much more stable provided that their errors aren't perfectly aligned. And that is a random forest model for you in its simplest form. If you'd like to see this coded out for you in simple Python, then don't forget to follow so that you don't miss part 2 of this video.